Okay, physics. So I wanted to go into how I use calculus along with work, and the important concept is that work is going to be a function of force times distance. So the important thing is that path matters, right? And hopefully this makes sense, right? So if I have my car here and I want to push it to this point, right, that's one distance that I'm going to travel, and that's going to take a certain amount of work to push it there. But if I decide I'm going to take a different route to get there, right, that's going to take more work to push that car there. So importantly in this is not displacement, which is the difference between where I start and where I end. Right? This is a distance traveled. So this is going to be the force over this distance. And it may be, right, so if I'm traveling up a hill and down another hill, it may be that the force that I apply here to keep it going is going to be less than the force that I apply here. So the force can be variable. And what I want to do is I want to add up, well, what's my little force times distance here? What's my little force times distance here? What's my little force times distance here? I'm going to add up all of these, so we'll call this a path integral. So I'm going to add up all of these as I go along it and figure out what is my total work. So I'm going to write this a little bit differently. So I'm going to write this as work being the integral of force times distance. We use dx or dr. So notice I still am using the dot product. So even though I have an integral here, it's still a dot product. So it's indicating how much of that force is in the same direction as displacement. So, if I'm going up a hill here and I'm applying a force like this, right? But if I'm going up a hill, I'm applying a force to the side, right? Then I've got to take that into account. So the key thing is that I use the integral to add up all of these little distances that I travel along the force. So this will get us the sum of the work. So we could go about it a couple different ways. You could have a variable force, or you could have a very variable distance, I guess. So let me go through a little example, and we can see. So suppose that I'm pushing a box. And I want to figure out how much work I put into that box, and the force that I apply has this function of distance. So a function at position. So this is the force that I apply at a particular position. So when I'm at the 0 position, I'm going to be applying 15 newtons. When I'm at the 1 meter position, I'm going to be applying 17 newtons. When I'm at the 2 meter position, I could plug in 2 and I'll be applying 19 newtons. So this is a variable force, and it varies along some function that we can describe. So we can figure out, well, what's the work that it takes to push a box from position equals 0 to position equals 10, say. So let's figure out what's the work that's involved with that. Well, I'm going to set this up as an integral. So my work is going to be a definite integral. I'm going to go from 0 to 10. And I want to do of my function 2x plus 15 times that little bit of distance that I'm traveling, right? So this is saying I'm going to go a little distance in here, see how much force that takes. I'm going to go a little further distance, see how much force that takes. And I'm going to add all those things up, and this is my integral for how I do this. Right, so I'm going to go through this. This is like the reverse of the power rule, so I'm going to figure out the math for this. So I'm going to have 2x. So remember how I'm going to do this. So I'm going to raise the exponent and add 1 to it, and then divide by that new exponent. So this is going to be x to the squared, and then I'm divide by that. So it's going to be 2x squared divided by 2. This is like x to the 0, so I'm going to add 1 to that. So this is going to be 15 times x to the 1 divided by 1. And I'm going to have some constant too. So I have to be careful, right? So if I don't have a definite integral, that constant matters, and this is just going to be able to tell me the change. It's not going to tell me the absolute value. So let's see, I can simplify this a little bit, right? So I'm going to have x squared plus 15x, and I'm going to have my constant, right? My constant is going to go away. So remember, so I'm going to evaluate this from 0 to 10 to see what I get. Right? So I'm going to plug in 10. So when I plug in 10, I get 10 squared plus 15 times 10 plus c. And I'm going to subtract from that when I plug in 0, which is going to be 0 squared plus 15 times 0 plus c at the end. So 0, 0. And notice now I have plus c and minus c. So my constant goes away when I worry about when I have definite integrals. Brief reminder, so I'm going to be left with this. So I'm going to be left with 100 plus 150, which is going to be 250. Again, work is going to be joules. All my energy is going to be measured in joules. Sometimes we write it as a Newton times meter, and sometimes we write it as kilogram meter squared per second squared. All of these mean the same thing, and so you're welcome to use any of them. So again, so we'll think about work as still being a dot product, and we'll think about work as still being a component of a function of force times distance, and the only complexity that we'll add into there is that I might have a variable force that I can then take into account. So anyway, I hope that helps, and we'll talk to you soon. Bye.